Let's do an example now to show state space versus transfer function eigenvalues. So in this example, I want to start with a system. X dot equals AX plus BU, Y equals CX. So I'd like to define my matrices. A is going to be a 3 by 3, and it's going to be in modal canonical form. So 1, 0, 0, 0, minus 3, 0, 0, 0, minus 6. B is equal to 1/10. 1/10, and then minus 1 over 6, and then 1 over 15. And my C vector will be 1, 1, 1. So with the system in this form, it's important to note that all the eigenvalues of A all have real parts, and those real parts are all less than 0. So the system is asymptotically internally stable. So that's good news. But what is the transfer function of this system? Well, in order to see what our transfer function is, we're going to go back to our definition of the closed loop system in terms of the transfer function. So the transfer function g of s is equal to c times si minus a inverse times b. So if you forgot where this came from, I encourage you now to go off and look at x dot equals ax plus bu. Take the Laplace transform sx minus ax equals bu, and remember that y equals c times x, and that g equals y over u. So you can use this system of equations, do a little bit of algebra, and then show that this ends up being your transfer function here. So if you want to do that for a minute, go ahead and push pause on this video. Once you've convinced yourself of this fact, you can come back. So with this definition now, I'm going to go ahead and take the matrices that I have. C is equal to 1, 1, 1. I have to find Si minus A inverse, which is actually not that hard, because Si minus A inverse is just going to be S plus 1, S plus 3, and then S plus 6. So this is the Si minus A part, inverse, and then times B. So B was 1/10 minus 1/6, and then 1/15. So taking the inverse of this diagonal matrix is actually pretty easy, but I'm going to go ahead and show you that this value, I can just show you the final result here. So the final value, after we multiply all the pieces together, if you're sort of wondering about your linear algebra, go ahead and press pause again until you can show this for yourself. So we end up with 1/10 times s plus 3, s plus 6, and then minus 1/6 times s plus 1 and s plus 6, and then plus 1/15 times s plus 3, s plus 1. And this is all going to be divided by s plus 1 times s plus 3 times s plus 6, because we need to divide through by the determinant. So a bunch of different pieces cancel one another out, and in fact we end up with a system g of s that's equal to 1 over s plus 1, s plus 3, and s plus 6, which is actually pretty remarkable. So, this being the case, after we add all these pieces together and subtract them apart and make everything come back and forth, is that we can look at this system here and check its stability. So in fact, this system, G of S, is bibostable. And all three modes of the system, from lambda, was equal to minus 1, minus 3, and minus 6. Each of these show up in the transfer function G of S. So this is the link, this is the relation between the modes of the system from the A matrix and how they show up in how the system responds in terms of time. So this is why we define the state transition matrix as e to the AT. We don't need B or C in order to see what our system's time response is going to look like in terms of stability. All we need to see is that the modes of the system are related to the eigenvalues, and the eigenvalues are related to the poles of the system.